Okay, we're going to do a little review of some calculus here. I think we're going to do it in two parts. First, look at some theory questions in the first part, and in the second part, we'll look at a couple of application problems. The application problems can include sketching, max-min, or related rate questions, or velocity acceleration questions. First off, let's just kind of review what you could see on the formula sheet. If you look here at the formula sheet, that's what I'm sharing with you. You get the derivative from first principles, which can show up, not often, but it can show up on an exam. So we'll look at an example of that. You're given that formula, and then you're just given a whole list of rules. So make sure you're aware of the rules that are there and the rules that are not. They're pretty much all there. I can't think of something that's not. And they do have the chain rule, the product rule, and the quotient rule in the theoretical ways, you know, with the u and u dv, dx, v prime, whichever way you want to look at it. They should all be pretty clear to you, okay? So make sure you're sure of you know what rules are available to you. And like I said, if you can think of one, let me know in class. I can't imagine there's any other rule up here you'd have to know. I suspect the ln rule isn't there, and neither is e to the x, but they're sort of contained right in here. You can see you've got derivative a to the x. Well, if a happened to be e, then ln e right here would be 1. Okay, so that would give you e to the x. And if a happened to be e here as well, this would give you 1 right there. That ln a would be 1, and so you'd end up with the derivative is 1 over x. Okay, let's share this to the iPad now. I'm just going to move over to the iPad, and we'll look at a couple of examples. Here we go. Okay, so the first example that I have is a first principles, okay? So first principles means to use the formula that you saw on the formula sheet. So what you're looking at to get the derivative function, let's call it y prime, is the lim as h goes to 0. It's f of x plus h minus f of x all over h, okay? We're looking not for the derivative at a point, but a derivative function, so we don't specify the value of x. We leave it as just x. And so now we take our function that we're given here, which is 1 over x squared, and since it's a fraction itself, I'm going to rewrite this as, instead of, say, I'll put it up here, instead of 1, everything divided by h, I will multiply f of x plus h minus f of x times 1 over h. That will avoid having fractions over fractions. So f of x plus h is 1 over x plus h squared, and f of x is just minus 1 over x squared. Okay, and we're taking the limit of this whole thing. Now, clearly, as h goes to 0, I'm going to have a 0 in here, and a 1 over 0. So that's an indeterminate form. The way we're going to do that, indeterminate form, is change its form by finding a common denominator. Notice I'm not multiplying out the brackets, because if I do, then the common denominator is going to be even more complicated. Not yet, anyways. Okay, so this becomes x squared, and this becomes x plus h, all quantities squared. Okay, so something like this. All right, so now, of course, we still have, you see, if you put h as 0, you get x squared, take away x squared, you get zeros here, and you get a 0 down there where it's 1 over h. So it's still a 0 over 0 case. And the way we're going to finish this off is by multiplying out those brackets inside here. Okay, that way I can see the x squared and the x squared will go away. I'll be left with terms involving h, and that will allow me to cancel this h out right here. Okay, because that's a denominator that's 0. We don't want that. That's the indeterminate part of the indeterminate form. So if I multiply this out, I'll get x squared minus 2xh minus x squared. The minus signs are coming from the fact that there's this negative sign here in front of the brackets. Okay? So now we have the lim as h goes to 0, 1 over h, and like I said, these x squared terms cancel out. Okay, and then now we can cross out this h here with 1 here and 1 in the h squared on the top. Okay, so that leaves us with the lim as h goes to 0, minus 2x minus h all over x plus h squared x squared. And I can see my little squareds got mutated here. We don't need a squared there. That's my mistake, talking and writing at the same time. And now you see as h goes to 0, we don't get that 0 over 0 anymore. We have a negative 2x minus 0 on the top, and the bottom, it's just x plus 0 squared x squared. So this simplifies to be minus 2x all over, well, it's x squared times x squared, or x to the fourth. So I'm left with a minus 2 over x cubed, and I believe that's what they want us to show. Yes, that's the final answer. So we've given them their answer as required. Okay, so all of these first principle questions are the same thing. You start out with the formula here. And you might want to rearrange it like this to avoid fractions over fractions, but you sub the x plus h into the formula, and your goal is to try and cross this h out on the bottom by doing whatever algebraic tricks that you like. Sometimes you're factoring, sometimes you're multiplying out, sometimes you're finding common denominators, like in this case. Other times you are rationalizing the denominator. That's pretty much everything I can think of in terms of those kind of questions. So if we look through those examples, you'll see some more different situations when you have to work with first principles. Okay, another sort of theoretical question here is finding the tangents. Okay, now you can't really expect to see a question on, for very many points anyways, in the HL syllabus that says find the equation of a tangent. Usually you have to do something more exciting with it. In this particular question, here we have to find the tangent to the curve on this restricted domain at x is pi over 4, and it turns out it's going to intersect the curve again. Okay, so I'm imagining some graph of tan x. It's a calculator question, so we can actually take a look at it. We will in just a second. I can see the graph of tan of x. Okay, so even though I have my calculator, maybe I'm doing the reading time of the question, I know that tan x between pi over 2 and minus pi over 2 looks like this. Okay, halfway at pi over 4, the tan of pi over 4 is 1. Okay, so there's some tangent line here. And apparently, well, it doesn't look like it by my graph, but apparently it's going to intersect the curve at another point. It has to be down over here someplace. So maybe this minus pi over 2 needed to be a little bit shifted over, but we'll see in a sec. As you see, it's a graph and calculator question, so we can always find that intersection point using the GDC, and we will, because it's probably going to save us some time. Okay, well, when in doubt, not too sure what to do, always take a first derivative. So the derivative of tan is sec squared x. To find the equation of a tangent line, I need the slope of this derivative at the interested x coordinate, pi over 4. So we're looking for sec squared at pi over 4. Now we have our GDC, so if you want, you could evaluate that on your graphing calculator. But for the non-paper questions, it might be a good idea to review what this is without a GDC. Okay, so it's 1 over cos of pi over 4 all squared. Cos pi over 4 is 1 over root 2. So this is 1 over root 2 all squared. I think you'll see that we're going to get a nice number like 2. Okay, so that's the slope of this tangent. So its slope is 2. Now we also need the y-coordinate. And we already said that the tangent of pi over 4 is 1. So therefore, the tangent line is always y minus y1 is m times x minus x1, where x1 and y1 are the point of tangency, and m is the slope. Okay, so this means y minus 1 is 2x minus pi over 4. If you want, you can simplify that. So this will be minus pi over 2 plus a 1. Okay, not a very nice equation. We want to know where it's going to intersect the graph at a second time. So what we need to do is make this equation 2x minus pi over 2 plus 1 for a point of intersection has got to equal the graph itself, which is tan x. And here's where I stop and I go, there's no way you can solve an equation that involves an x and some sort of trig function analytically. It can't be done. So this is it where we need to use our graphing calculator. If we don't, we'll spend eons of time not finding the solution. So let me share on the screen the graphing calculator. Okay, so we'll put that on here. On my desktop, I've got a GDC. Okay, here it is here. Okay, and so what I've drawn here is I've drawn the graph of tan x, and then my equation line, which you can see here, is tan x. Let's see if I can just, maybe what we can do here. Now we can just share. This might look a little bit better. There, we just share the graphing calculator. So we've got tan x, and then we've got the equation of the tangent line, 2x minus pi over 2 plus 1. Now, a couple of things to note. Make sure you're in radian mode, otherwise it won't be the right graph. And the window, well, they told me that it should be from minus pi over 2 to pi over 2. Okay, and then I just use values of -4 and 4 as my y values. So I get a graph like here, and I can check a couple things out right off the bat to feel good about my exam. One, I can see that if I pick a value here, and I do pi divided by 4, you can see the tangent line that we've drawn does appear to be tangent at the line at the point pi over 4. So that's pretty good. What we're looking for is this point over here. To find that, we have to calculate, and then it's intersect, 5, intersect, and it's asking me to pick some curves. Well, the first curve I'll pick will be the tan x, so I'll push enter. And then, oh, it automatically goes to the other curve. There's only 2 curves on the screen, so it goes to the other curve. I'll pick that to be my second curve, okay? I don't push enter too quickly, because if I push guess, it's gonna give me the point of tangency. What I wanna do is go closer to the point I'm looking for and the other point of intersection. So I'll just keep going here a little bit closer and closer. Okay, that's pretty close. I'll push enter, and it should zero in. Ooh, error, no sign change. Let's go to. Didn't find the sign change, so let's graph it again. This is getting interesting. Let's try that one more time and getting a little closer and see if we can find the calc and intersect. First curve. Here's my second curve. Maybe we weren't close enough to that intersection point. Okay, there. That's pretty close there. Now, if I push enter, what happens? Aha, it finds it. And it tells me, so by, oops, we'll say, oh, by GDC, you can't see that. Let me just share my screen back to the iPad. So let me share, I'll be right with you in a sec here, and we'll put that coordinate in there, okay? While I'm doing this, you should remember that we want 3 significant figures, okay? So if I go, I can take a peek here at my graphing calculator. You can see that the point was 1 minus 1.257, blah, blah, blah. So for 3 significant figures, we write negative 1.26 for the x coordinate. Now, if they wanted the y coordinate, I'd write that again as well, but I believe the question was just asking us for an x coordinate, okay? So back here, yeah, just the x coordinate. So we're good there, okay? If you want, you could also include that on your graph here. 1.26. Okay, one more question before we finish off, and that's implicit differentiation. Big popular topic in the syllabus is the implicit differentiation questions. Often every year there'll be one either on paper 1 or paper 2. Maybe we can take a quick look at both of these, Nick. Number 11 says find the gradient of the normal. Okay, so gradient, if you're coming from a school that uses the word slope, its slope is the same thing as a gradient. And you see, since I have a y squared, this is implicit differentiation. So in order to implicitly differentiate, we must differentiate both sides with respect to x. Okay, so it's 2y, y prime, and then here what we have is a product rule. So that's 3 times y plus 3x y prime, and then this is just minus 20x 0. Okay, I need to find the slope of the tangent, well, the normal. So first off, the slope of the tangent, and then slope of the normal is minus 1 over the slope of the tangent, the negative reciprocal. But to get the slope of a tangent with implicit differentiation, what I need is an x coordinate and a y coordinate. Now stop for a sec. A lot of people will try and solve for y prime right here in this equation. okay? But it didn't say to find the equation for the derivative function in terms of x and y. I don't really need to find that equation. I just need to get the value of y prime when the x is 1, okay? So when x is 1, I need to find out what the y coordinate is, okay? So I'm going to put that into my y function. So I get y squared plus 3 times 1y minus 10 times 1 squared is 0. In other words, y squared plus 3y minus 10 is 0. That equation will factorize and give me two values of y. So I get y plus 5y minus 2. So I know y is 2 or negative 5. Okay, now you can just, this iPad will behave here. We can probably scroll back to see the question. It says that y has got to be greater than 0. Often when there's two values, one is just y is 2. So the point of tangency is 1, 2. That is going to go into our gradient expression. So we have 2 times this y value of 2 for this 2, y prime, plus 3 times 2, 3 times 1, y prime, minus 20 times 1 is 0. So 4y prime plus 6 minus 3y prime minus 20 is 0. So 7y prime is equal to 14. 6 minus 20 is negative 14, becomes a positive 14 on the other side. So y prime is 2, okay? Notice I didn't solve for y prime first and then sub the values in. I sub the values in first and then solve for y prime. Makes things a whole lot easier. Now that's the slope of the tangent. So the slope of the normal is the negative reciprocal, or minus 1 over 2. Okay, and that solves that question there. So if they're not asking for anything more than a gradient or a slope, no matter what form they're in, just sub your x and y value into the equation you get when you first do your implicit differentiation and solve. Okay, the last one here says find the coordinates of all the points on the curve where dy dx is equal to 0. This one's slightly different now, okay? So let's just write down the equation. It's x squared plus y squared minus 3y is 10, and then scroll up here. What we want to do is find all the points on this curve where dy dx is equal to 0. And I believe the question said points, so there could be more than one solution. Okay, so let's solve by first differentiating. So 2x plus 2y, y prime, minus 3y prime is 0. Okay, so now we need to solve for the y prime because I don't have an x and a y coordinate to plug in. Okay, so I solve for the y prime. Let's work on that here. I'm going to factor out a y prime from these two expressions right here. That leaves me with 2y minus 3, and we'll bring the negative 2x to the other side. Okay, so we have 2y minus 3 is equal to negative 2x. So minus 2x over 2y minus 3. Now, I want this to be equal to 0. To make the fraction equal to 0, it must be that the numerator is equal to 0. So that means that minus 2x is 0, or x is 0, okay? So if x is 0, to get the y coordinate, I have to sub back into the original equation. So I end up with something like that. And once again, I'll bring everything to the other side. Hey, that's very similar to the other equation. It's almost the same one as before. Oh, they just changed the plus y to minus 3y. I think they could come up with different questions, but I guess not. So this is y minus 5 and y plus 2 is 0. So we get that y is negative 2 or 5. Now this question, if we scroll back up and take a look, had no restrictions on x or y, so anything goes. So that means there's 2 points where the gradient is 0. 0, negative 2, and 0, 5. Okay? And that would solve that kind of question there. Now, you couldn't really use your graphing calculator for an implicit differentiation question because the GDC doesn't allow for implicit functions. But we can take a quick look to get an idea what just happened here by looking at Desmos. So let me just clear this out here. Okay, and we can put that equation we just had. I believe it was, oh yeah, x squared plus y squared minus 3y. I think I can remember that. X squared plus y squared minus 3y, and I think it was equal to 10. Okay, so if we go in here and make that equal to 10, it's really just a circle, interesting enough. And we said that the slope of the tangent was 0 at the points 0, -2, and 0, 5. And if you look, sure enough, at 0, -2, and all the way up here at 0, 5, the tangents are flat. Okay, so that's essentially what we're doing there. Okay, we're going to pause the video for now, and you can probably try some of the theory questions in the calculus review section, and then we'll come back a little later on and do 3 or 4 word problems with calculus. Okay, so we're going to come back in just a moment.